I'm Lillian. Today I'm going to tell you the story of stellar evolution and binary stars. In our universe, trillions of stars coexist. They live lives not unlike our own. They're born, they have growth spurts, they shrink and they die. Scientists call this process stellar evolution. Have you ever been told it's not the number on the scale that counts? Well, it is for stars. When a star is born, one factor determines what the rest of its life will look like: mass. A star's mass, or how much stuff it's made up of, is essential to its survival. To these celestial bodies, mass is fuel. Stars burn themselves up to light our sky. Clearly, stars' bodies don't exactly work like humans. Unlike us, members of star kind spend most of their lives in a phase called the main sequence. During this phase, stars have plenty of fuel. They chug along pretty happily, sometimes warming planets like ours. But this cheerful status quo can't continue forever. Near the end of its life, when a star starts to run out of fuel, it expands to become a red giant. After this giant phase, stars collapse into themselves, either trumpeting their demise or quietly fading from memory. Every star story is governed by one rule: the more mass it has, the more quickly it evolves and dies. Why this gross inequity? Massive stars have shorter lives because all stars are born with a finite amount of life fuel. Sure, massive stars are born with more fuel, however, these behemoths burn through what they've got pretty rapidly. Thus, they actually wind up with shorter lifespans. Now let's add some new characters to our tale. We tend to think of stars as lonely, stoic balls of burning gas. But this isn't usually the case. Most stars are born with companions, and a system of two of these companion stars revolving around each other is called a binary star. In these systems, stars have been known to orbit each other at up to 310 miles per second, like colossal bowling balls whirling through space. Many of the stars you know are actually binary, including Sirius, the brightest star in our sky. Enter Algol, a binary which baffled scientists for years. When humans discovered Algol, we found a system of a low-mass red giant and a high-mass main sequence star. Why did this pairing appear to us so unnatural? Remember the rules of stellar evolution. How could a low-mass star go giant before its high-mass twin? To answer this question, astronomers had to look closely at Algol's path through a gravitational lens. Gravity is the force that holds binary stars together, but it has dramatic side effects. This includes the formation of gravitational fields called Roche lobes, de facto spheres of influence around each star. When a star in a binary system goes giant, it can overflow its Roche lobe. Excess mass funnels into the other lobe and falls onto its companion star. This is likely what happened to Algol. The giant was originally more massive, but when it ballooned, it lost much of its mass to its companion. Thus, today we see a high-mass main sequence star twirling with a low-mass giant. Sometimes these binary mass transfers can lead to titanic explosions, including type 1 supernovae. As we seek to further explain these phenomena, we will discover a more complete picture of the physics of our universe.